Chapter 3 includes describing what makes an element and how are different elements different from each other, and in explaining that, we will go into what makes up an atom and the different parts of the atom, and using that to explain how these elements are different from one another. So an element is just a pure substance in which everything else is built upon. Um, so you're probably familiar with many of the elements, um, many metals you come across: gold, aluminum, silver, iron, things like that, and then some non-metals like carbon and oxygen and things of that nature. And so, if you recall from the previous chapter, they discussed what the elements and how elements are pure and different from one another, and they have certain physical and chemical properties. So, each element is represented by a different symbol, and it consists of either one or two letters. And you have some examples in the bottom table there. It will always start with a capital letter, and then the second letter will always be um, lowercase if there is a second letter. And you should be able to recognize some of the more common elements, and being able to remember what the symbols are for these common elements, such as carbon and nitrogen and oxygen, and a select few others. So here's just some common ones. So we have sulfur, and sulfur is the capital S. We have aluminum with the capital A and lowercase l, which would seem to make sense because we're just using the first or second first two letters. But then we get to something like gold and silver, and so and those are much different. Which gold has the atomic symbol of Au, and silver is Ag, and that's just because of the those symbols were based off of their Latin names. So here is just a quick learning check, and like I said, you should be able to recognize some of the more common elements and the common elements from their groups, and we'll kind of go into that once we start talking about the periodic table in the next parts of the chapter. But here we have you should just be able to find calcium on the periodic table, and then be able to find its atomic symbol. And calcium is symbolized by choice B, capital C, lowercase a. So remember that if there's a second letter, that must be a lowercase a. Number 2 for nitrogen. Nitrogen is symbolized by the choice A, capital N. B would have been for neon, and C would have been for sodium. So, choice A is correct for number 2. And then number 3, iron. Iron, again, is one of those special ones. So it's actually not going to be IR. It's actually going to be choice C, Fe. Fe is the atomic symbol for iron, and so again, that's just one of those that's based off of the Latin names. And here it shows you, in case you need that. And so in the next learning check, we need to do in the opposite direction. Select the correct name for each of these symbols. And so S you find on the periodic table, and B, choice B, sulfur. Then we have number 2, P. P is actually the atomic symbol for choice C, phosphorus. It's not potassium. It actually is phosphorus. And then choice number 3, Ag, was in our example in the previous slide, and Ag is the atomic symbol for silver. And so now we'll kind of go over the periodic table. The periodic table can be found on the front inside cover. It's um, nothing you'll have to memorize, but you need to know how to use it and be able to find things from the periodic table and use it for other information as we'll go on through the chapter. Um, but this will help you greatly if you know how to use it. And so here you see the periodic table, and just want to take note of these group numbers and group names and period numbers, and we'll talk all about these in this coming chapter. And we'll also talk about why we have these different colored boxes and things of that nature. So the periodic table, you saw those numbers on the top of the periodic table and on the side of the periodic table, and those will help you be able to find certain elements and figure out some information from that. And so the numbers on the top are called the group numbers, and that's because the um, each column is called a group, and it's a group because it contains elements that have similar properties. And we'll talk about why they have similar properties when we talk about the different particles of the atom. But right now, you just need to know that they have similar properties. Um, and then we also have the rows, or what we call periods. The periods are the horizontal rows of the elements. Um, and those are pretty straightforward. They're counted from 1 through 7, from top to bottom. And how you can one helpful way that I remember the difference between periods and groups is that you write a sentence in the horizontal direction. You write it from left to right, and so and you always end the sentence with a period. So um, and that's one way that may be helpful for you to remember which are groups and which are periods. And so here you see, you know, see down the periodic table, we have group 2 right there. It's the second column, and period 4, which is the fourth row. And so we have these group numbers, and if you looked at those group numbers, you would have seen two different markings. Um, we had 1 through 18, and then we also had 1A, 2A, and then all the way through 8A. And so these are used for different reasons, but they give you the same information. So if we are in, when we use, when we're not using the letters, we use just 1 through 18. So that's just a straight counting of columns. And so the first column is group 1, second column group 2, second column, third column group 3, so on and so forth until you get to all the way to the right hand side where you get the group 18. The other markings you might have saw was with A's and B's. And so where we have the transition metals, we use the letters B's, those B letters after the numbers, and on the upper columns, not including the transition metals, we use the letter A's, and so we'll count 1 through 8A, and when we're not including those transition metals, then we'll just use the B letters for the transition elements on the lower portion of the periodic table. And so, but we get the same information. It's just used to signify which group people are referring to. And so the first group is what we call the alkali metals. And so this group includes lithium, sodium, potassium, rubidium, and cesium. These are very reactive elements, and their reactivity increases from top to bottom of the group. And so as you get further down, it gets more and more reactive. Um, and we'll soon learn that this group has only one electron in its valence shell, and so that may mean nothing right now, but it'll make more sense later on. You will want to take note that on the top we don't have hydrogen, so hydrogen is a different and it's actually not a metal, and so it's not part of the alkaline metal group because it's not a metal, and so we don't actually include it into it. Next, we have the group 7A or group 17, whichever you'd like to use. Both mean the same thing, but that is the halogen group. And these are also reactive elements, and these include fluorine, chlorine, bromine, iodine, and astatine. And this is a non-metal group, and we'll talk about that shortly. And we'll also learn that this group reacts similarly because they have 7 electrons on the outside uh, shell, and that'll make more sense again later on, but I want to include that now so you are familiar with that. The group 18 or group 8A is the noble gases, and here we have helium, neon, argon, krypton, xenon, and radon. Um, and so these are very unreactive gases. Don't really find them in combinations with any other elements. Typically, they're just by themselves, and um, and so we don't have to really. And we'll learn soon that they don't react with very often because they have a completely filled outside shell of electrons. And so here we need to identify the elements based on their location on the periodic table. So if we look at a periodic table and we um, look for group 7A or group 17, that is the halogen group. And then the period 4, we would have to go down to the 4th row and we'd find that would actually be bromine, choice A. And number 2, group 2A or group 2, so that would be the alkaline earth metals, and then we'd be looking for period 3. So period 3 is the we see Mg, which signifies magnesium. And now we have number 3, group 5A or group 15. So that brings us to the nitrogen group. And if we're looking at period 2, that's actually going to be nitrogen, choice C. All right. And so earlier that we had these different colors of the periodic table. We have the blue, the green, the yellow portions. And so that's just to signify the metals, the nonmetals, and the metalloids. And if you notice, the metals are on the left-hand side, and we have the nonmetals typically on the right-hand side, with the exception of hydrogen. And so then we'll talk about why that is later on. And then we have in between the two groups is the metalloids, and they're just kind of have both metal and non-metal properties. So they kind of just in between. And so metals are, typical of what you think about with metals. They're shiny, they're uh, ductile. You are able to make wires out of them. You're able to bend them. They're good conductors of heat electricity. We use those things in wires to pass electricity through. We use them in our pots and pans, and because they're good conductors of heat. Um, Whereas metals are not very shiny. They're not ductile or malleable, so they're very brittle. If you try to bend them or do anything with them, they'll typically break if they are in a solid form. Um, and they don't conduct heat or electricity very well. And then we have the in-between ones, the metalloids. So metalloids are um, they're not especially great conductors, but they're better than nonmetals, and they're just not as good as metal. They're better than nonmetals, not as good as metals for conducting either heat or electricity. So um, just in between, figuratively and literally. And then most metalloids are used for semiconductors. If you are familiar with semiconductors, typically metalloids are used. Here's just a summary of the different characteristics of the three different types of elements that we're discussing. And so, you just can see that, we have totally opposites when we're looking at metal and non-metal. And then we have just the in-between in metalloids. And so here are just elements that you find in an adult person. You have the major elements that you typically think of when you think of organic compounds and living things. You have hydrogen, carbon, nitrogen, and oxygen that makes up, you know, all living things. That's what we have in our amino acids and our proteins and everything like that. So, and then we have element minerals that we need a lot of. We have a lot of sodium and potassium and calcium and magnesium. And then we have other elements that we have very little of in an adult, and we have some of those transition metals and a few of them metalloids and a couple of non-metals. So here we just need to identify whether these elements are a metal, a non-metal, or a metalloid. So you should be able to identify these if you're given a blank periodic table just by its location on the periodic table. You would have to be able to identify if it's a metal, non-metal, or metalloid. So here we have sodium. Sodium is on the left-hand side of the periodic table, and so that is a metal. Chlorine. Chlorine is group 17, all the way on the right-hand side of the periodic table, and that is a nonmetal. Silicon is right along that stair. If it's on that stair, it's going to be a metalloid, with the exception of aluminum. But here, it's on that stair in between the metals and nonmetals, and so it's a metalloid. Iron is a transition metal, and you can just think about our iron itself, and it's definitely a metal. And then we have carbon. Carbon is a non-metal. It's on the right hand side of that periodic table. So in this learning check, we are to match these elements to their location in the that they are describing in the periodic table. So in number 1, we're looking at metals in group 4A or group 14. And so we just find that group 14 or 4A, and we are underneath that carbon group, and we just need to find the metals. So the metals are going to be in the bottom portion of that. So the bottom 2 is going to be tin and lead, or SN and PB, choice A. Non-metals in group 5A or group 15 brings us to the nitrogen group, and we need to look at, and this one's if we're looking at the inside cover, it's nice because it makes the different colors for the metals and non-metals and metalloids. But if they weren't colored, you'd have to be able to tell that as well. So here the nonmetals are going to be in the upper right hand portion, and so it's going to be the N and the P, nitrogen and phosphorus. So it's going to be choice B. Now we got number 3, metalloids in group 4A or group 14. So we need to be along that stair for in between the metals and nonmetals. And so here we have the Si and the Ge, and so that would give us choice B. So this brings us to the atom and the structure of the atom, and it's going to be important in explaining some of the reactivity and some of the properties that are observed with the different elements. And so one of the first theorists about atoms was John Dalton, and he came up with this theory of that atoms are these tiny particles that make up all of matter. So anything that has um, mass and takes up space is made up of an atom. And these atoms are able to combine with other atoms to make different types of compounds. And um, each atom of the same type is called an element, and they are all similar in their properties. And these elements are going to be different from all other elements with their in terms of their properties. So they're not going to be exactly alike. So an atom of the same type is an element, and each element has its own unique properties. And lastly, a chemical reaction is when these atoms are rearranged and recombined uh, or broken apart. And so, through other theorists and other experiments, um, it was found that these atoms are actually made up of other tiny particles, and these tiny particles um, are protons, electrons, and neutrons. And all of these particles have a charge and have a mass. And a proton has a positive charge, and you can remember that because positive and proton both begin with the letter P. So positive protons. Neutrons. Neutrons are neutral or no charge. And then electrons have a negative charge. So similarly, as you find with magnets, uh, that with magnets, if you put two of the same poles together, they repel each other. And the same thing here with these same charges. So if you put two positive charges together, or you try to put two negative charges together, they repel each other. But if you put two opposite charges together, they're going to attract. Like you would put a north and south pole together, they would attract. And so, as they always say, opposites attract. So that is in the case of here as well. And so protons are attracted to electrons because of their positive and negative opposite charges. In a very famous experiment, Rutherford's gold foil experiment, um, he found some interesting facts about the atoms. And so what he had done was he had actually shot positively charged particles at a very thin piece of gold foil. And when he shot these particles, he found that most of these positive particles went straight through the atoms and went through that foil and ended up on the other side. And then very few of them were actually deflected into different directions. And so what he had concluded was that the atom uh, has a very small, dense, positively charged, what we call a nucleus in the atom. And so if these positively charged protons hit that positively charged nucleus, then they would be those particles would be deflected off and not be able to go straight through the foil. But since so few of them went and were deflected, that meant that most of the atom must be empty space, um, and so that's why he found that many of those particles went straight through the foil, and the very few that did hit the atoms, they were of opposite charge. They were of the same charge. The nucleus positively charged. The particles that were shot at were positively charged. They were repelled from each other, and so they did not stick together. Rather, they, deflected off. And so here is a diagram of his experiment. And so you see the container of some type of radioactive element in the lead container. It shot these radioactive particles, which are basically just positive particles at that foil. And you see most of the dots landed straight through the foil, and a few of them were deflected off. And so the basic structure of the atom is that the nucleus, that small dense part, contains the protons and neutrons. And because neutrons do not have a charge and protons have a positive charge, the nucleus as a whole has a positive charge. And then on the outside of the nucleus is where we find the electrons. And the electrons orbit around the nucleus and can take up a lot of space in which that there's in the space that they're moving around in. They're actually very small particles, but they can be found in a large area. So you don't know where they are exactly, but they're just can be found in a large area. So since atoms are so small and and using such a large numbers in our scientific notation, or our large exponents in our scientific notation, they have developed a new scale for atomic masses and for these subatomic particles, and we call it the atomic mass unit, or AMU. And the AMU unit was just based off of a particular isotope of carbon, which is carbon 12. And we'll talk about an isotope and what an isotope is later on in this chapter. But what you just need to know is that an atomic mass unit is just based off of carbon 12. And so a proton and a neutron is the heavier subatomic particles. They have an approximate mass of 1 AMU. And the electrons are very small and have very small mass, and an electron's mass is approximately 0.00055 atomic mass units. And so if you're putting all of this together, you see that a proton and a neutron are both found in the nucleus. It's a very small part of the atom. It's a very dense part of the atom, and that's where most of the mass is contained, is in the nucleus. The electrons are very small particles. They have very small mass, but they can be found in a large area around the nucleus of the atom. And so they're just moving around and orbiting around a large volume around the nucleus. And so here's just a summary table of the three different particles. We have these symbols of the different subatomic particles. We have their charges, and their masses in atomic mass units and where they are found in the atom. So here we just need to look at these different characteristics and determine whether it's describing a proton, neutron, or electron. And so here, number one, found outside the nucleus. So there's only one um, subatomic particle found outside the nucleus, and that is the electron. Number two has a positive charge. So positive, you see it begins with P, so you should think positive proton. So number two is proton. Is neutral. Number three is neutral. So neutral is neutron. Begins with that same first syllable, neutral, neutron. So number three is neutron and found in the nucleus. So this can be uh, two of them. Right? The only one outside the nucleus is the electron, and the other two, the proton and the neutron, are both found in the nucleus. And there you go. And so here, in this part of the chapter, we'll talk about um, some more properties of this atom, including atomic number and mass number. And looking at the periodic table, you saw the symbols of each of these elements, but there's a lot more information that you can gather as well, but, in addition to its location. And so you also see the atomic number. So each element has its own unique and specific atomic number. No two elements have the same atomic number, and as you go through from left to right and then from bottom to top, if you feel like you're reading a paragraph, that's how the numbers go. The atomic number is defined as the number of protons in an atom. And so that is what makes each element unique from each other, is that each element has its own number of protons. So that just means that if an atom has one proton, it has to be a hydrogen. It cannot be any other element. If an atom has 16 protons, it must be sulfur. It cannot be any other element. And in this case right here, if we have sodium, its atomic number is 11. It has 11 protons. If we find an atom in nature that has 11 protons, it must be sodium. It cannot be any other element. And so here is the same thing as I was describing in the previous slide, describing that in these examples, hydrogen has an atomic number of 1, and so every hydrogen always has 1 proton. And same thing with carbon with 6 protons, and copper with 29 protons. And so if we were given these different examples and we had to figure out the number of protons, what we would have to do is just look at the element, find it on the periodic table, find the atomic number, and that is the number of protons. So here we have nitrogen. Nitrogen has an atomic number of 7, and so that means it has 7 protons. A sulfur atom, number 2. Sulfur is found as number 16. 16 atomic number means it's 16 protons. Barium is Ba, and so we find barium on group 2, on second to last one in group 2. We found the atomic number of 56. That means it has 56 protons. So, as we discussed in the previous section, a proton has a positive charge and an electron has a negative charge. So, if an atom is neutral, then the positives and the negatives must balance out. So, we need to have just as many positives as negatives. So that means they need to have just as many protons as electrons. Positive protons, electrons are negative. And so we need to have an equal number of each in order for their charges to cancel out. Okay, so In our example here, we have aluminum. Aluminum has 13 protons and 13 electrons. Its net charge is 0 because protons are positive. We have 13 positives and electrons are negative. That's 13 negatives, and so they cancel each other out. Mass number. If you recall from the previous section, most of the mass of the atom comes from the nucleus and comes from the protons and the neutrons. And so the mass number is equal to the sum of the protons and neutrons because most of the mass is from the protons and neutrons. So that's where the number comes from. So if you look here, are just some models of the atoms. If you look at the lithium, lithium has an atomic number of 3 and actually typically has 4 neutrons. And so you look at that picture, you see 3 red protons and 4 blue neutrons. And then you would notice that there's 3 electrons because it's a neutral atom. And so the positives must equal the negatives, and so the protons must equal the electrons. And so here we'll find 3 protons and 3 electrons, and in this case we have 4 neutrons. In our example on the right, carbon, we have 6 protons because it has an atomic number of 6, and that means we have an equal number of electrons, which is also 6. And in this example here, we find that we have 6 neutrons. So in this learning check, it says that an atom of zinc has a mass number of 65. So how many protons are in a zinc atom? So if we need to look at the number of protons, we don't even need to look at the mass number. For zinc, all we need to look at is where it is in the periodic table. So if you look at the periodic table, it's in group 12 and period 4. We find it with Zn, and it has the number 30, so it's an atomic number of 30. Atomic number is the number of protons, and so here we have choice A, 30 protons. Then, how many neutrons are in the zinc atom? Well, this one we have to use that mass number of 65. If we know we have a mass number of 65, that means protons plus neutrons. If we know we have 30 protons, then the remaining of that mass number must be the number of neutrons. So we must subtract the 65 with 30, and we're left with a remainder of 35. And so that means that we have 30 protons, we would have 35 neutrons, and if we added those together, that would give us a mass number of 65. So number 2 is choice B. And then number 3. What is the mass number of a zinc atom that has 37 protons? Well, we know that zinc must always have 30 protons, and if it has 37 neutrons, if we add those two together, that will give us the mass number. So 30 plus 37 is equal to choice C, 67. And then there it is written out for you. And here's another learning check. An atom has 14 protons and 20 neutrons. What is its atomic number? So its atomic number, 14 protons. Atomic number must be 14. Protons and atomic number are the same thing. So choice A. What is its mass number? So mass number is protons plus neutrons. So we must add those two together. 14 plus 20 is equal to 34. Choice C. And what is this element? So to determine the element, it's all determined by the number of protons and its atomic number. So we look on the periodic table and find the number 14, and we find it with the silicon, Si. symbol, and so we have choice A. And so in this part of the chapter, we will discuss isotopes and atomic mass. So in the previous part of the chapter, we mentioned the word isotopes, and so isotopes are just atoms of the same element, but have different mass numbers. So if you recall, if we have an element, each element of the same type must have the same number of protons. So the only thing that's going to differ is the number of neutrons. And so one way to signify different elements is through this notation seen on the bottom. And so in this symbol, it tells you the symbol of the element. It tells you its atomic number on the bottom number, and then it tells you the mass number on top. And so the nice part about this is when it's set up this way, you can just actually set up the subtraction operation right here to find the number of neutrons. So magnesium would have the only 12 neutrons. So 24 minus 12 equals 12 neutrons. And so, and that's for this particular isotope of magnesium. And so if we had magnesium of a different isotope, we would still use the Mg symbol because it's still magnesium. We would still use the same atomic number of 12. That would never change if we have magnesium. The only thing that would change would be the mass number. And so if that mass number changes, then the number of neutrons changes. So when we have isotopes and are referring to different isotopes, we must be able to distinguish them from each other. And so that's why we use these. This is one way of showing the different isotopes, and there's another way that isotopes are also identified, but in this case is much easier to see. And so in these symbols, we always have three parts to it. We always have the symbol of the element, and usually that's written fairly large, and then as we use the atomic number on the bottom left hand corner, and the mass number goes in the upper left hand corner. And so you must be able to recognize how to use this, what information this is revealing to you, and what other information you get out of it. Like, for example, like the number of neutrons. And so here's just some other examples given. So in the left-hand example, we have oxygen. Oxygen always has an atomic number of 8, which means 8 protons. Since it has 8 protons, it must have also 8 electrons if it's neutral. And then we have a mass number of 16, and so if we do 16 minus 8, that would give us 8 neutrons. For the middle one, phosphorus. Phosphorus always has an atomic number of 15, and so if it has 15 protons, it must also have 15 electrons. And then it has a mass number of 31, and so if we have a mass number of 31, we subtract 31 and 15, and we get 16 neutrons. And last but not least, we have the zinc on the right hand side, and zinc has an atomic number of 30, and so then it must also have 30 electrons to be neutral, and then 65 minus 30 is equal to 35 neutrons. And so here we can try out the same thing. We talked about the carbon-12 isotope, and there are other carbon isotopes. You might have heard of them. Sometimes they are used in the medical field as tracers. You might also heard of carbon dating, in which they can use carbon isotopes. And so here we have we need to determine how many protons, neutrons, and electrons each of these isotopes have. And so in each case, we are dealing with carbon. Carbon, no matter if it's an isotope or not, we will always have 6 protons. So each of these isotopes has 6 protons. And if they are neutral charge, they must have the same number of protons as the electrons. So each one must also have 6 electrons. So then for carbon 12, well, the only thing that remains is number of neutrons. And so for carbon 12, we subtract 12 and 6, the mass number minus the atomic number, and we get 6 neutrons remaining. For carbon 13, it's 13 minus 6, which gives us 7 neutrons. And then for carbon 14, it's 14 minus 6, which gives us 8 neutrons. And so that is what you see here. And so here we will try to write down the nuclear symbols for these atoms. And so number 1, we have 9 protons. So right off the bat, we know we have 9 protons. So we find the atomic symbol or the element that has 9 protons, then gives us fluorine. And so fluorine, if it has 9 protons, it's going to have 9 electrons if it's neutral. And so we can write a capital F, and we write a 9 in the lower left-hand corner. And then we have 10 neutrons, so we have to add 10 and 9 together. That gives us 19 on the upper left-hand corner. And I'm going to just go down to the next page so you can see that. Number 2, we have chlorine. That was determined because we have 17 protons. We find the symbol or the element that has the atomic number of 17. So we look on the periodic table, and there we see Cl, chlorine. And then we have, for the mass number, we have to add 20 and 17, which gives us 37. So the mass number goes in the upper left-hand corner, 37, and then the atomic number goes on the lower left-hand corner, which is 17. And then for number 3, we have 47 protons, so that's an atomic number of 47. And so that would we would have to look on the periodic table for silver or Ag, and we look there and we find it there. And then we have 60 neutrons. So if we add 47 and 60, that gives us 107. So that means our mass number is 107. So the mass number goes in the upper left-hand corner, and the atomic number goes on the lower left-hand corner. And so that's where we put the 47. Learning check. Which of the following pairs or isotopes are the same element? And so if they are the same element, they must have the same number of protons or the same atomic number. And so they have to look on that bottom left-hand corner and see which ones match. And so if we look at A, B, and C, the only one that has the same number of protons or same atomic number, that is choice B. Then if we look at number 2, in which of the following pairs do both atoms have 8 neutrons? So in this case, we would have to do the subtractions. So in A, we have mass number of 12 and atomic number of 6, so that gives us a remainder of 6 neutrons. So there, A cannot be correct. Choice B does the same thing. 12 minus 6 is 6, so that cannot be the correct answer there. And then the only one left would be choice C. And if we do it out, we have 15 minus 7, which gives us 8. And then the second column gives us 16 minus 8, which is 8. And so both of them have 8 neutrons. And there you see it. If you look on the periodic table, you see the atomic number, you see the symbol, and then you see a number that usually has a bunch of decimals. and that is actually the atomic mass of an element. And so the atomic mass is the mass that is an average of that atom that is um, weighted proportionally to their isotopes. So many elements have uh, can have two, sometimes three, sometimes even more isotopes. And if you weight those averages proportionally to how often they are found in nature, that gives us the atomic mass. And so many people, many students confuse atomic mass and atomic number, or atomic mass and mass number. So um, the atomic mass, the numbers on the periodic table, is not often used determining the subatomic particles. It's often used for other calculations. Um, so uh, be careful in not confusing those properties. One way that you can remember or kind of think about it is that if you're confusing those values, you can never have a decimal or a fraction of a proton, neutron, or electron. So if you're ever saying how many protons, neutrons, or electrons you have, it can never be a decimal. All right, so so here we have a table, and we see these different elements and what isotopes there are of these elements and their atomic masses. And so here we see that, for example, carbon. Carbon has uh, three different common isotopes: carbon 12, carbon 13, carbon 14. And um, the atomic mass is a weighted average, and we see that it's very close to 12. And so that would lead us to believe that carbon 12 is the most popular isotope. Fluorine is very nice because it only has that one isotope, and so it has an atomic mass of 19 AMU. Sulfur is not so nice, and it has four common isotopes. But if we look at the atomic mass, it's 32.07, very close to the 32 mass number, and so that would lead us to believe that sulfur 32 is the most common isotope. And then lastly, if we look at copper, copper has an atomic mass of 63.55. Again, that is a closer number to 63 than to 65. And so that would lead us to believe that the copper 63 is more common than copper 65. So we mentioned the weighted average of isotopes, and this kind of just shows what that means visually. And so in this example, we look at chlorine. Chlorine has an atomic mass of 35.45. So using the same reasoning we said before, that would mean that chlorine's isotope 35 is probably more popular. And here it actually gives you the percentages. Chlorine 35 is found in nature 75.76% of the time, whereas chlorine 37 is 24.24% of the time. And you see the larger bar for the chlorine 35. And so because that atomic mass number is closer to the 35, that leads us to believe that chlorine 35 is more prevalent in nature. Luckily, in this class, we won't have to do these calculations. It's not required of us. So we're not going to go in depth into it, but this just kind of shows you the reasoning behind, or the reasoning of explaining where this atomic mass comes from, and but I will say no more. I don't want to confuse anyone uh, if we don't need to go any further. So this is just if you were curious of where the atomic mass comes from. The same thing can be done of magnesium. Magnesium, again, not as nice as some of the other ones. It has 3 isotopes, and so the magnesium has an atomic mass of 24.31, very close to 24. So that means 24 is the probably more prevalent isotope. That's all you really need to know for this class. So here, if we look at the periodic table, if we're given these elements, we need to find the atomic mass for each of these. So calcium is found in group 2, period 4, symbol Ca, and that is the atomic, which has the atomic number of 20 and the atomic mass of 40.08. Aluminum is found in group 13, period 3, symbol Al, atomic number of 13, and so that's the atomic mass of 26.98. Number 3, lead. Lead is group 14, period 6, Pb. Pb has an atomic number of 82, and then we have an atomic mass of 207.2. Barium, Ba, group 2, period 6, atomic mass of 137.3, and iron, Fe, group 8, period 4, and we have an atomic mass of 55.85. And here you find what we have just described. And so here it asks us to find it's given us the atomic mass of chlorine, which is 35.45, exactly what's given on the periodic table. And so based on that information and that information alone, which would we expect to be the most prevalent isotope, which one we find in larger amount in nature. And so since atomic mass 35.45 is closer to 35 than it is to 37, that would lead us to believe that choice A, chlorine 35, is seen more often. But we don't have to do these types of calculations, but you should be able to read into some of that information as far as which should be more popular. So in section 6, we will talk about and focus on electrons and what information the number of electrons gives us, and information we need to know about the electrons, because the electrons really is important in explaining the chemical reactivity to many atoms and elements. And so, as we said before, these atoms have a very small, compact nucleus with most of the mass, and with the neutrons and the protons. But then a large volume of space around it contains these electrons, and these electrons explain the physical and chemical properties of atoms. And these we describe these electrons as being in different energy levels, and so each electron is not exactly the same as the other in terms of energy. There's physically they're the same, but depending on where they are and where they're found, they have different amounts of energy. And we use these principal quantum numbers to describe where they are, how close they are to the nucleus. And so the level that's closest to the nucleus just has a quantum number of 1, and so these are electrons that are closest to the nucleus. If you go up one level, it is going to be in the second quantum number or n equals 2. And then you go to the next level, be 3 and 4. Well, the important part is that you remember that they begin with 1 and they go up by whole numbers. And you kind of think of it as like floors in a hotel. You're going to start on floor 1. And so as you go up in the energy levels, that means the energy of the electrons goes up, and that the electrons are getting further away from the nucleus. And as you get further from the nucleus and as you go up these energy levels, you can actually hold more electrons. And so it's showing you basically a bookshelf, and so you see in shelf 1 you can only have the two books, and then in the second shelf you can have more books, and if they had books in the third shelf they would even be able to hold more books than that. And so um, it has the possibility or capability of holding more electrons, not necessarily they always will have them. And within these different energy levels, there are sub-levels. And so we can have a certain number of electrons in each energy level, and we can put them into different sub-levels. Now, you will want to know that in these sub-levels, each sublevel will have electrons of the same energy. And we identify these sublevels by these 4 letters, S, P, D, and F. And the number of sublevels that are allowed within the energy level is equal to whatever the principal quantum number is. So if we are in energy level 1, we are allowed to have 1 sublevel. If we are in energy level 2, we can have 2 sublevels. If we're in energy level 3, we can have 3 sublevels, so on and so forth. And so here is showing a picture of that. And so in energy level 1, we can have 1 sublevel, and that first sublevel, it will always be S. In energy level 2, we can have 2 sublevels, and so if the first one will always be S, and then the second one will be P. In the third energy level, we can have 3 sublevels, and the first one will be S, and then it will be P, and then it becomes D. And then last one we'll use is energy level 4. We can have 4 sublevels, and then we have first S, then P, then D, and then F. So just as the different energy levels had different amounts of energy, the different sublevels also have different amounts of energy, and so the order just goes from S, P, D, F. So they just as the order they fill up, just as we saw in that S was first, P was second, D was third was D, fourth was F. That is how the energy goes as well. So S has the lowest amount of energy, F has the greatest amount of energy, and so each sublevel can be divided into orbitals. So we've started with the energy levels, or the principal quantum numbers, and they're divided into sublevels, and these sublevels are now can be divided into orbitals. And so orbitals are just regions where we have the greatest probability of finding these electrons. These electrons are moving very fast. They're impossible to pinpoint their exact location at any one time. And so that's why we're just saying this is the highest probability of finding them. Each orbital has their own unique three-dimensional shape, and each orbital can hold up to 2 electrons. And so the s orbital is a spherical shape, so you can just remember S is spherical. It is centered around the outer nucleus. The sphere gets bigger or larger as you go up in the energy level. So um, if we have the principal quantum number of 1, and that s orbital in the energy level 1 is going to be smallest. Whereas if we compare the s orbital in the fourth energy level, it's going to be largest. Um, s orbitals can only hold 2 electrons, and these 2 electrons will always have opposite spins. And so that just means that no one electron in an atom is going to be exactly the same. They're not going to be found in the same energy level, sublevel, orbital with the same spin. The p orbital is first found in the second energy level. These orbitals always have to have a two-lobed shape, much like tying two balloons together in the middle. Each p orbital can hold 2 electrons. These p orbitals align themselves along each three-dimensional axis, so the x-axis, the y-axis, and the z-axis. So we can have 3 p orbitals. Each one can hold 2 electrons, so we can have a maximum of 6 p orbitals in the p sublevel. And the size of these orbitals increases as we go up in energy level. So each sublevel contains a specific number of orbitals. We have the s sublevel can have 1 s orbital. The p sublevel can have 3 p orbitals. The d sublevel can contain 5 d orbitals, and the f sublevel can have 7 f orbitals. And so you just want to remember, we start off with energy level, and then we start off with sublevels, and then we go to orbitals. And so remember that the number of sublevels possible is always equal to the number of energy levels. And so in the example on the bottom, we have an energy level of n equals to 2. That means we can have a possibility of 2 sublevels, which would give us the 2s sublevel and the 2p sublevel. And then we got to give the 2s sublevel, we can have the 2s orbital, and that could give us a total of 2 electrons in that orbital. And then we have the 2p orbitals and the 2p sublevel. And so they can align themselves in the x, y, and z axis. And so that gives us 3 different 2p orbitals. Each of those can hold 2 electrons, and so we could have a total of 6 electrons in the 2p orbital. And so this is a nice summary in the in showing how many electrons can be held in each sublevel or each orbital. And you can notice that the s orbital or the s sublevel can always have 1 orbital and can have a maximum of 2 electrons. The p sublevel can always have a maximum of 3 orbitals and can have a maximum of 6 electrons. The d sublevel can have a maximum of 5 orbitals and have a maximum of 10 electrons, and the f sublevel can have a maximum number of 7 orbitals and a maximum of 14 electrons. And so here it's asking us to indicate the number and type of orbital in each of the following. And so here we have the 4s sublevel. So if we're on the 4s sublevel, that means we have a 4s orbital. And so the s orbital can have 2 electrons. The 3d sublevel we would find the 3D orbital. There's five 3D orbitals. Each one can hold 2 electrons, which can hold a maximum of 10 electrons. And then the last one, n equal to 3. N equal to 3, we can have 3 different sublevels: the S, the P, and the D. So we could have 3S, 3P, and 3D. Okay, so with that last one, just remember if we can have a maximum number of sublevels equal to the quantum number n. So here it's just asking us a variety of questions, and number one is asking us the number of electrons that can occupy a p orbital. So no matter what type of orbital it is, it can only hold a maximum of 2 electrons. So this is going to be choice B. Number two is asking us how many p orbitals in the 2p sublevel. So we can there can be the px, the py, and the pz. So that would be 3 different p orbitals. And so that's choice C. D orbitals in the n equal to 4 sublevel. And so we can have 5 different d orbitals. So that'd be choice C. And then electrons that can occupy the 4f sublevel. And so the 4f sublevel can have 7 different orbitals. Each orbital can hold 2 electrons, so 7 times 2 is equal to 14. Choice C. So in the previous section, we had talked about a lot of the backbone information in describing where we can find electrons. And so in this section, we'll actually be applying it and figuring out where the electrons are specifically for each of the different atoms or elements. And so we talked in the previous sections in how to determine how many electrons an atom will have. And so here we're going to fill up these energy levels that we have been talking about with these electrons. And so in order to fill these up, we have to fill them up in order of increasing energy. So we always want to start from the lowest energy and work our way up. Atoms, much like people, want to exert as little energy as possible, and so that's what needs to be done, is in order to fill them up with the least amount of energy. And so we'll always begin filling up with the quantum number of n equals to 1. And as we go up into other quantum numbers, and we have other sublevels and orbitals, we need to fill them up from S, then to P, then to D, then to F. So as we discussed in the previous section, S has the lower amount of energy and F has the most, and so we fill them up in order of S, P, D, F. Here you see the a diagram showing in the increasing of energy. So it goes from 1s to 2s to 2p, 3s, 3p. And then interestingly, then instead of going to 3D, it actually does go to 4s. It does get a little tricky in that way. But we'll kind of go into how to use the periodic table in determining what to fill up. And the order in which to fill up the orbitals and sublevels. We typically use an orbital diagram to show where the electrons are in the atoms. And so they are just boxes to symbolize each orbital in each of the sublevels. The electrons are symbolized by arrows in the up and down vertical directions. And as we fill them up, you want to make sure that if you pair the electrons up, they must have opposite facing arrows. So we will discuss many of the rules that go along with filling up these orbital diagrams. So in filling it up, we mentioned that we must fill them up from the lowest energy levels and orbitals first. Um, when we are in a particular sub-level, then we must fill up these sub-levels with one electron in each orbital with the electrons arrows in the same direction before we pair them up in the other direction. And when we do pair them up, we must make sure that the arrows are in opposite directions, symbolizing electrons with opposite spins. And so here we look at carbon. Carbon has 6 electrons, and so we fill them up in order from 1s, then to 2s, then to 2p. And so we first fill our 1s with 2 electrons. We have them facing in opposite directions. Then we fill up the 2s with 2 electrons facing in opposite directions, which brings it up to 4. So we only have 2 remaining electrons. And so here we start filling them up, the 2p orbitals. We fill them up singly before we can pair them up. So we get 2 boxes with 1 arrow each, and we must make sure that these boxes have the arrows facing in the same direction. And so if we were to ask to draw orbital diagrams for each of these following elements, it'd probably be easiest to show you what we would do and then explain it. So nitrogen has an atomic number of 7, and so if it's a neutral atom, then it must also have 7 electrons. We fill it up from 1s, then to 2s, then to 2p. We can fit 2 electrons in the 1s. We give them opposite spins. Then we have 2 electrons in 2s. We make sure we give them opposite spins. That gives us up to 4. That means we have 3 remaining electrons. So we put up 1 electron or 1 arrow in each of the 2p orbitals with the arrows facing in the same direction. Number 2 is oxygen. Oxygen has an atomic number of 8, which means that we would have to have 8 electrons. So we fill up the 1s with 2 electrons, 2s with 2 electrons, as we had done before. Then with the 2p orbitals, we fill them singly first with arrows in the same direction, and then we have 1 more electron, and we have to pair up one of the 2p orbitals. And so we just make sure to give the paired up electron the opposite spin, so put the arrow in the opposite direction. The last one, magnesium. Magnesium has an atomic number of 12, which means we have 12 electrons as well as protons. So we fill up the 1s, we fill up the 2s, and then we fill up the 2p, and so we still have 2 remaining electrons. Then we move on to the 3s, and so then we pair up the 3s, 2p, the 2 3s electrons in the 3s orbital. Oftentimes we use electron configuration to describe where the electrons are in as far as which sublevels that they are in and how many electrons are in each sublevel. So in order to come up with the electron configuration, you can list each of the energy levels and corresponding sublevels, and then using superscripts you write down how many electrons are in each of these sublevels. So if we were looking at neon has an atomic number of 10, which would mean it has 10 electrons as well as protons. And so we first fill up the 1s orbital with 2 electrons. Then we fill up the 2s orbital with 2 electrons. And then lastly, we fill up the 2p sublevel with 6 electrons. And so that brings it to a total of 10 electrons. And so period one has only 2 elements, hydrogen and helium. These 2 electrons are the hydrogen has one 1s electron, helium has 2 1s electrons, and so here's just a nice little table that shows you the orbital diagram, and then also shows you the electron configuration. So hydrogen has one 1s electron, and helium has 2 1s electrons. In period 2, we have lithium, we also have beryllium, boron, and carbon, all the way down the line, nitrogen, oxygen, fluorine, and neon. And lithium will have has an atomic number of 3, so that means it has 3 protons, but in this case we're looking at 3 electrons. And so we know that 2 of them have to be in the 1s orbital, and then we have 1 remaining in the 2s. Beryllium has an atomic number of 4, so that means it has 4 protons and also 4 electrons. 2 of them are in the 1s orbital, and then the remaining 2 are in the 2s orbital. And the trend continues on. So instead of when you get further on in the periodic table, and if you are asked, the electron configuration for something on the bottom portion of the periodic table, that would be a lot of writing, a lot of writing of the different energy levels or sublevels and the electrons in each. And so there is an abbreviated electron configuration, and how this is done is once you write down or figure out the electron configuration, you can abbreviate the portion that represents the a completed sublevel. So the noble gas electron configuration previous to where you have previous to your element that you are describing. So in this example, if we look at chlorine, chlorine has the 1s2, 2s2, 2p6, 3s2, and 3p5. So the noble gas that is previous to the chlorine, if you follow your numbers, you go down, go to the left, you go from chlorine, you go down your period all the way back to sodium, and then you end up back up to neon. Neon is the last noble gas before you get to chlorine. All right, and so you can, and neon's electron configuration is the 1s2, 2s2, 2p6. So you can abbreviate that completed sublevel and the completed energy level with the neon in brackets. And so all you have remaining is the 3s2 and 3p5 electron configuration after the neon or Ne in brackets. And so this table goes through many of the examples from all the elements from lithium to neon, and shows the orbital diagrams for each of them, the electron configurations for each of them, and the abbreviated electron configurations. And so for each of those are all in period 2. Those are all elements in period 2. And so the only previous noble gas before period 2 is found in period 1, which is helium. And so helium is the last noble gas before you get to period 2. When we look at the elements in period 3, we have the all the way from sodium to argon. That's period 3. So the previous noble gas to period 3 is the noble gas in period 2, which is neon. And so if you look at the abbreviated electron configurations for all of these, they all have neon because neon is the last noble gas in period 2 before we get to the period 3 elements. And so in this learning check, we're asked to find the correct electron configuration for nitrogen. And so going down the list, A cannot be correct because it totally missed using the 2s orbital. And so it has to be in order from 1s to 2s to 2p, so that one cannot be correct. B, 1s2, 2s2, 2p6. We have all the orbitals or sublevels, but we have way too many electrons. If we look at nitrogen, nitrogen has an atomic number of 7. And so it should only have 7 protons and 7 electrons. Here we have 10 electrons, so it's too many electrons. That cannot be correct, and so we're left with choice C, which is correct. Number 2, the correct electron configuration for oxygen is, again, A is similar to the A in the previous question. It skipped 2s, so that cannot be correct. Choice C is much like choice B in the previous question. There's too many electrons. Oxygen should only have 8 electrons. This one has 10. And so we're left with choice B. Choice B is correct. And then number 3, the correct electron configuration for calcium is. And so the correct one should be choice B. And so I could understand if it's confusing that we went from 3p to 4s instead of filling up to 3d. If you'll just have to remember that and remember that diagram that was previous in the section. But 4s is lower in energy than 3d. So that is why it gets filled up before the 3d. And so in this learning check, it asks us to write down the electron configuration and abbreviated configuration for each of the following. So we'll just kind of show the answer and go through explaining it. Chlorine, if you look for chlorine, it's in period 3, group 17. And so there you fill up your 1s. So you have 1s2, you fill up your 2s, so you have 2s2. You fill up your 2p, so you have 2p6. You fill up your 3s, so that's 3s2, and then you're left with 3p5. And then chlorine is in period 3, so you look for the noble gas in period 2, and that gives you neon. And neon ends at 2p6, so then you're just left with neon in brackets, 3s2, 3p5. Sulfur is much like the chlorine, except you have one less electron. And so you find that you have 1s2, 2s2, 2p6, 3s2, 3p4. Again, it's in period 3, and so you're going to have to use the neon as the noble gas before we get to sulfur. It's in neons in group period 2, as sulfur is in period 3. And so you're left with neon in brackets 3s2, 3p4. And then lastly, we have potassium. Potassium is in group 1, period 4. And so if we're in period 4, we're probably going to be in the 4th energy level. And so we just fill up our 1s2, 2s2, 2p6, 3s2, 3p6. And then instead of going to 3D, we have to go to 4s. 4s is lower in energy, and we have only one. So 4s1. And then potassium was in period 4. And so then to do the abbreviated configuration, then we have to go to noble gas in period 3, which is argon. So we have argon, and then we're left with 4s1. To figure out where you're going to end your electron configurations, the periodic table can be arranged and broken up into different sub-level blocks. And so groups 1 and 2 is called the S block because you'll end your electron configurations in the S sublevel. Groups 3A through 8A, or group 13 through 17, that is your P block because you'll end your electron configurations in the P sublevels. The transition elements, that's your D block. So your electron configurations will end in the D, and the lanthanides and actinides, those ones that are kind of cut and pasted onto the bottom of the periodic table, that's your F block. So this slide just kind of puts together what that last slide was describing, and so if you print off a periodic table, you can probably just mark it up in this way to maybe help you remember where some of these portions are. And so again, S block groups 1 and 2. That's why hydrogen is all the way on that left hand side. Helium is part of the S block, but it's on that on the right hand side. And then we have the D block transition metals, we have the P block and most of the non-metals, and then we have the F block, the lanthanides and actinides. And then this is just the diagram that's provided in the book and just shows you the, again, the order of filling up the sublevels. And so in using these sublevel blocks, how you want to kind of work through it is you want to be able to first find where your element is on the periodic table, and then fill up the sublevels in order going across each of the periods. So first fill up your 1s, and then you're going to go down to the 2s block, and then you fill up your 2s, then you're going to go to the 2p in the p block. You fill up your 2p's, and then you're going to go to the 3s block and then fill up that, and then you're going to jump over to the 3p block and then fill up that, and then you're going to go back to the 4s and fill up that block, and then that's where you finally hit, after you get to the 4s's, then that's where you finally hit the 3d's. So you start filling up the 3d's, and then you go back to the 4p's, and so you just kind of work through those blocks. And so here, looking at silicon, you first, as we were describing before, we have our period 1. We have to go through the 1s block, and we fill that up. Then we get to period 2, and we need to go through our 2s and our 2p blocks, and so we fill those up. And silicon is in the 3p block, so we fill up our 3s's and we start filling up our 3p block, and that's what we must end in our 3p block. And since it's in group 14, it's only 2 into the p block, we only have 2 3p electrons. Here's a table that kind of goes past the 3p block because of that whole difference in filling up the 4s's before you get to the 3d's. So you can see that there. There are a couple oddities in chromium and copper in which you fill up the D's before the S's, and some classes make you memorize that. We're not going to be remembering that. I just won't use those as examples or questions on an exam or anything like that. Here's another example. It passed the 4S block. This is manganese. Manganese is period 4, group 7, Mn, and it has 25 electrons. And so we have to go through our S block. So we have 1s2. We have to fill up our 2s and our 2p blocks. We fill up our 3s and our 3p blocks. Then we fill up our 4s block, and then it's in the 3d block. So we're going to finish in there. And so we get to fill 5 of those electrons in the 3d orbitals. And so we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d5. If we abbreviated that, we would go to the previous noble gas. We're in period 4, so that would bring us up to argon. And so argon would have replaced all the way from 1s2 to 3p6. So here, the question is asking, what are the last two sublevel blocks in the electron configuration for CO, or cobalt? Cobalt is found in period 4, group 9, and so that's in the D block, and that's going to be the 3D block, and so that's going to be the last one. And then before the 3D block is the 4S block, and so we get choice C. C is the correct answer there. Number 2 is, what are the last 3 sublevel blocks in the electron configuration for tin? Sn. Tin is a period 5, group 14, with the 50 atomic number, so 50 electrons and protons. And so that's in the P block, and that is found in period number 5. And so that means we would be in the 5p, and then we would have 4d and 5s. So it would be 5s2, 4d10, and then 5p2. So that would give us choice B. So you can maybe remember that the D's is always one number behind the period number. And those are the answers right there. And here's asking us, using the periodic table, write the electron configuration, abbreviated configuration for each of the following elements. And so we'll just kind of look at the answers and go through explaining them. So the first one is zinc, and zinc, it's found in group 12, period 4, and we would work our way through 1s2 and then through 2s2, and then we're past the whole second period, so 2s2, 2p6, we're past the third period, so we have 3s2, 3p6, then we're in the fourth period, so we have to go 4s2, and then we're all the way at the end, so 3d10. And then we're in period 4, so we have to find the noble gas in period 3, which is argon. So argon will replace all the way from 1s to 3p. Strontium is found in the group 2, period 5. And so there we would have to fill up the first period, 1s2, then the second period, 2s2, 2p6, the third period, 3s2, 3p6, the fourth period, 4s2, 3d10, 4p6, and then lastly you fill up 5s2. And then strontium is in group period 5, so the noble gas in period 4 is krypton, so krypton would take the place of everything from 1s2 to 4p6. And then lastly, we have iodine. Iodine is group 17, period 5, and so it'd be pretty much the same thing as the strontium, except that we have to go past it, and so we have to fill up the 4d10, and then we have to have 5p5 is in the p block. And so similarly, it's in period 5, so the go find the noble gas in period 4, which is krypton, and so then we're left with krypton in brackets and 5s2, 4d10, 5p5. Here's asking us just do the find the symbol for these elements that have these particular characteristics. So the abbreviated configuration for argon 4s2 3d6. So we would have to go to argon, and then we fill up our 4s2, so we're up to calcium, and then go 6 over in the D block. And so we would bring us to iron, Fe. Give the symbol of the element that has 4 3p electrons. So 4 3p electrons. So we find period 3, and in the p block we have aluminum, silicon, phosphorus, and sulfur is the fourth one over. Number 3, 2 electrons in the 4d subshell. So 4d subshell would have to actually be in period 5. D is one behind the period number. And so we would start with the Y and move on over one more to the Zr, zirconium. And then we have the electron configuration 1s2, 2s2, 2p6. So we have our 1s field, our 2s 2p field, our 3s 3p field. We get to 4s, which brings us to calcium, and 3d2, so 2 over. So we have Ti, or titanium. And in the next chapter, we'll be looking at, our next section, we'll be looking at trends in the periodic table. So what other information can we get based on the placement of the elements in the periodic table as far as certain properties and to that nature. And here we have to introduce the idea of valence electrons. So we've been kind of talking about valence electrons indirectly. Valence electrons are the outermost electrons that have the highest amount of energy in an atom. And much of the chemical properties of elements are associated with the number of these valence electrons. And it's just related to which group these elements are found in. And so if you look in the case of phosphorus, phosphorus is group 5A or group 15. Well, indirectly, that tells you how many valence electrons it has. It's in group 5, it actually has 5 valence electrons. And that's because in the outermost shell, we have the 3s2 and the 3p3 electrons. And so we have 2 and plus 3 is 5 in the 3 energy level, the third energy level, and so that is considered the 5 valence electrons. It's very easy to figure out not only from what period it's in, but if you're just given the electron configurations, if they're an abbreviated version, then whatever is not in the brackets is considered the valence electrons. So like in calcium and strontium, they're in group 2, they have 2 valence electrons, and they're in the 4s2 and the 5s2 respectively orbitals. And so so whatever is not in the brackets is the valence electrons, and then the number of valence electrons is pretty much associated to what group number it's found in. And sometimes the electrons are symbolized by dots if they're drawing electron dot structures, and sometimes it's used to show how things or other elements or atoms are bonding to uh, these atoms. And you can basically the number of dots is just the number of valence electrons. So whenever you see these electron dot structures, it's just associated to how many valence electrons there are in these atoms and elements. The only one exception, I guess, is the helium. Helium has only 2 valence electrons, even though it's in group 8. But the reason why it's there is because you're only allowed 2 you're only allowed 2 electrons in the 1s orbital, and that 1s orbital is filled. So it is a noble gas because its outermost shell is filled. So in this learning check, it's asking us to identify the number of valence electrons for each of the following elements, and it's pretty much done by looking at what group number it's found in. And so oxygen in number 1 is found in group 6, 6A, or group 16. That means it has 6 valence electrons. Aluminum is in group 3 or group 13, and so it has 3 valence electrons. And then chlorine is found in group 7A or 17, and that's 7 valence electrons. And it's pretty much as easy as that, just finding out what group number it's in, and that's how many valence electrons it has available to it. Here it's asking us to do pretty much the same thing. So calcium is in group 2, and calcium, Ca, has 2 valence electrons. All the electrons in group 6A or group 16 have 6 electrons, valence electrons, and then tin is Sn, and that's found in group 14 or 4A, and so that's 4 valence electrons. And there's the same. Here, if we're looking at the number of valence electrons in each of the following, well, one way to think about it is where was the last noble gas? So the last noble gas, number 1, would be 1s2, 2s2, 2p6, which is neon, and so that just leaves the 3s2 and the 3p1 remaining, which gives us 3 valence electrons. Number 2, same thing, and so we can just chop off the 1s2 to the 2p6, and we're left with 3s2, so that's 2 valence electrons. And then number 3, we have 1s2, 2s2, 2p5, and so we don't fill up that p orbital, so we have to keep the energy level 2 and just chop off the 1, which is the helium. So helium is the 1s2, and so we're left with 2s2, 2p5, which is 7 valence electrons. We mentioned electron dot symbols previously because of the table had introduced it. So electron dot symbols or electron dot structures just indicate the number of valence electrons and symbolizes them as dots around the symbol of the element. And so in this case, magnesium has 2 valence electrons, and so in drawing the electron dot structure for magnesium, we just put 2 dots around magnesium. And so all elements in groups 1 would have 1 dot, all elements in group 2 would have 2 dots, groups 3 would have 3 dots, and 4 would have 4 dots. And so in 1 through 4, you represent them as having dots as single dots. You don't have any of them paired up. And then when we get through 5 through 8, then you have you can start pairing them up. So you can have up to 4 pairs. And so as saying before, group 2 will always have 2 valence electrons, and that's what it's just kind of showing here. So just using the group numbers as determining how many valence electrons you have, and then that determines how many dots you should put in your electron dot structures. So X dot, just a single dot, is the electron dot symbol for it's any one that would have a found in group 1, And so any one of these found in group 1, so we find sodium and potassium in group 1, so A and B would technically be correct for number 1. And then number 2 is the electron dot symbol 4. And so here we have 2, 4, 5 dots, and so that would be group 5. And so any of the elements found in group 5 would be acceptable, and that would be choices B and C. And there it is. So using those group numbers and number of dots and time to find the correct answers. So this brings us to start discussing some of the trends found within the periodic table. And the first one we'll discuss is atomic size. And atomic size is the size of the atom, and that's pretty much described as from the atomic radius. So describing the distance from the nucleus to the valence electrons. So how far are those outermost electrons? And so the radius or the size increases as you go down the group and as you go to the left on the periodic table. And as we go down a group, we're adding more energy levels, and as we add more energy levels, they're getting further and further away. Um, and then as we go to the left of a period, we would have, since we're on the same period, we have all these electrons within the same energy level. But as we have the one thing that does change in the energy level is the number of protons, and so protons are attracted to electrons. And so if we have more protons, there's going to be more attraction. If there's less of protons, there's going to be less attraction. And so um, since there's more protons on the right-hand side of the periodic table, those would have a smaller radius or a smaller size. And since there's less protons on the left-hand side, there's less protons, less attraction, and so they are going to be greater in size. And so that's what as you see here. So the largest atoms are found on the bottom left-hand side of the periodic table. And so if we were to compare these elements, which one we had to determine which ones are smaller. So if we look at lithium and potassium, since potassium is further down on the group, then it means it's going to be larger. Number 2, if we look at potassium and bromine, so they're within the same period. So whichever one has less protons is going to be larger because there's less attraction. So that's going to be potassium yet again. And then for number 3, phosphorus and chlorine. So we have, again, atoms within the same period. So whichever one's to the left or has less number of protons is going to be larger, which is phosphorus. We'll also talk about ionization energy. So ionization energy is just the amount of energy it takes to remove these valence electrons from an atom. And so you think about it, we already discussed how large the atoms are, and so if they're larger, these valence electrons are going to be further away. So if the electrons are further away, then it's not going to take as much energy to remove them because there's less attraction. So it follows pretty much the same trend in that atoms that are larger on the bottom left-hand side are going to be easier to ionize because those electrons are further away and take less energy to remove those electrons. And so that's the general trend. It's not concrete, but it does follow that trend more times than not. And so that's just showing you a little chart of that. So ionization energies of metals are low, just because metals tend to be larger in radius, and so there's less attraction, and so it does not take as much energy. Whereas metals are typically smaller; they are more attracted to the nucleus, and so usually takes more energy to break those bonds or attraction. Metallic character increases when an element loses its valence electrons more easily. So if it's more easily ionizable, it has more metallic character, and so it follows the same trend as ionization energy. So that bottom left-hand side of the periodic table should be the most metallic character, which is what we see here. And so those are the ones that are going to be larger in radius. Those are the ones that are going to have easier to lose the electrons. There's not as much attraction, and so they're the more metallic character. And so these just kind of summarize the different trends that we had talked about. And so it's a nice little summary table. And so here it asks us to select the correct element. And so here it's asking us to figure out which one has the higher ionization energy. And so higher ionization energy would be whichever one's furthest up on the periodic table or to the right on the periodic table. So here we're looking at lithium and potassium. Lithium is higher up, and so that would have a higher ionization energy. It's a smaller radius. The electrons are more close to the nucleus and be harder to break that attraction. So lithium would be the correct answer. Number 2 is potassium and bromine. So potassium, bromine are the same group, and same period. And the one, if you remember, radius would increase to when you get toward potassium, and bromine is actually going to be smaller, and so the electrons are going to be closer to the nucleus in bromine, and so that would be harder to break that attraction. So bromine would have a high ionization energy. And then phosphorus and chlorine, again, very similar. Chlorine would have a higher ionization energy because the electrons would be closer to the nucleus and harder to break that attraction.